working on various aspects of quantum Hall problems with Sri Raghu, and since then he has been a postdoc at Princeton working with Duncan Haldane and Ravin, who is also visiting us, and he would be talking about phase transitions in quantum Hall systems today, and tomorrow he would also talk about another aspect of the quantum Hall problem, the Half-Landau level and the non-Fermi liquid. So Prashant, looking forward to the talk. Oh, just one thing, please use this microphone for asking questions since this talk is being recorded, and the online people, just raise your hand and I'll try to tell you at an appropriate moment to ask your questions. Okay? Yeah.
Thank you, Shubhra, for the introduction, and thank you for coming to the colloquium. I'm going to talk about topological phase transitions in the quantum Hall effect. I will give you two examples of topological phase transitions. I will try to explain why they are interesting and why they are a fundamental problem in quantum condensed matter physics. Let me start by mentioning my collaborators. The first part of this talk will be based on my PhD work with Sri at Stanford. And the second part, I hope I can give you at least some brief overview of that, will be based on my work with Ravin Bhatt, who coincidentally happens to be in the audience. The other collaborators who were involved in the first part of the work are Mike Mulligan, he's a professor at UC Riverside, Pavel Nosov, who is at Stanford University. The seminar tomorrow will be based on my work with Duncan Haldane at Princeton, and these are my other collaborators. So let me start by giving you a brief overview of why quantum Hall transitions are interesting, these topological phase transitions. Let me first tell you about what topological phases are. Topological phases of matter, they are ordered phases of matter. And we know about other ordered phases of matter, the ones that break symmetries spontaneously at low temperatures. However, these are distinct from them in the sense that they do not break any symmetries. I will define them for the purpose of this talk to be zero temperature thermodynamic limit ground states, which have an energy gap to the first excitation. So they are gapped. And they cannot be adiabatically connected to trivial product states without going through a phase transition. So how do we distinguish these topologically ordered phases from other phases, like insulators, like paramagnets, for example? So they can be distinguished from them using topological invariants. They have robust edge states between vacuum and the phase. Moreover, they can have fractional quasi-particles. They can have ground state degeneracy, which depends on the topology of space. Further, they can have long-range entanglement. So here is an example of a fractional quasi-particle. Suppose we have two particles, and suppose we are in 3 dimensions to begin with, and I take one particle around the other in a loop. Now, if I am in 3 dimensions, I can take this loop, move it out of the plane, and then contract it to a point. So then if I were to look at the many-body wave function, what happens is that because I can contract it to a point, the many-body wave function must come back to itself. So it must get either a phase of 2 pi or 4 pi or so on. And this is equivalent to 2 exchanges. So if the phase is 2 pi, an odd integer times 2 pi, that's a fermion. And if it is an even integer times 2 pi, that's a boson. However, suppose now we are in 2 dimensions. In that case, I cannot contract this loop to a point without passing through the singularity at the position of the other particle. So I can get more general excitations called anyons. And in that case, the many-body wave function does not have to come back to itself. It can get a phase of exponential I 4 pi times s. S is the spin of the anyon, and it can be fractional. There are many examples of these topological phases, like quantum Hall phases, which I will be concerned with in this colloquium. There are spin liquids, topological insulators in 3 dimensions, held in phase in 1 dimension, and so on. In this talk, we are interested in studying topological phase transitions, which are, let me define them as the phase transitions which involve which involve topological phase at least on one side. So to begin, let me first remind you the usual Landau-Ginzburg-Wilson paradigm of studying phase transitions. So this is the story that has been developed for studying spontaneous symmetry breaking transitions. It was realized in the 60s and 70s that you get scale invariance. There is a diverging correlation length. So there is a length scale in the system which diverges near the transition. And I define that correlation length as C, and G is my tuning parameter, and G critical, GC, is the point at which the phase transition happens. So my correlation length diverges with an exponent nu at the transition. And the general philosophy of studying this type of phase transition is to write down an order parameter which can fluctuate in space and time, and write down a free energy functional using this Lagrangian. For example, for superconductivity, it looks like this. We have time derivatives and space derivatives. We have a mass, and we have an interaction term 5 to the 4th. And you can see if G is bigger than G critical, mass is positive. That is a disordered phase. So it's not a superconductor. However, if G is less than GC, you get the Mexican head potential, and that leads to superconductivity. A third point, which will be important in a bit, is that if I add randomness disorder, like impurities in the system, these transitions are stable to the impurities or Cohen's disorder of random mass kind. So suppose I make this mass random in space. If the Harris criterion is satisfied, which means that nu, this critical exponent, times the number of space dimension, if that is bigger than 2, then this is stable. So how about topological phase transition? So what is different in this case? In terms of general philosophy, it's not different, but you get more rich objects to play with in these cases. For example, we can have emergent non-local excitations such as vortices. We can have emergent gauge fields at these transitions. We can also have topological terms which give rise to interference effects between different topological configurations. Moreover, disorder, the Cohen's disorder, can be crucial as several transitions will take place through quantum percolation. I will define this quantum percolation later on in the talk, so wait for it. Interactions and correlations are important at critical points in general, especially in low dimensions. For example, in the previous slide, I had this 5 to the 4th term, that's an interaction term. So these are important in general. However, many topological phases, like the fractional quantum Hall phase in quantum Hall systems, they are results of strong interactions to begin with. So it's hard to understand these transitions without having interactions between particles. Moreover, we have at low temperatures also the spontaneous symmetry breaking phases. So we can have competition or interplay between topological phases and the usual spontaneous symmetry breaking phases. Overall, one gets a very rich physics, which involves topology, disorder, interactions, and symmetries. And the two examples I will present will be different combinations of these 4 elements. To begin, let me start by explaining to you the basics of quantum Hall effect. So the system that we consider here is 2-dimensional electron gas. So that's 2 dimension. And we apply a strong perpendicular magnetic field to that 2-dimensional electron gas. We can write down a Hamiltonian for the electrons, which is just quadratic dispersion, p square over 2m, but with a magnetic field. And curl of this capital A is the external magnetic field. So capital A will be my electromagnetic gauge field that an experimentalist can control, for example. Classically, what one gets is cyclotron orbits. Electrons start going in circles in the bulk. However, at the edge, these cyclotron orbits get reflected. So you can see they are chirally, they are moving in only one direction. So they are moving anti-clockwise, and they are confined at the edges. So you get these edge states classically. However, I will be interested in the quantum problem. So when we do quantization, what one gets is the Landau levels. So these Landau levels are at energy n plus a half h bar omega c, so they are equally spaced in energy. Moreover, the number of states in each Landau level is extensive. So each Landau level is extensively degenerate, and the number of states, single particle states in a Landau level is given by number of flux quanta passing through the system. This is inherently a quantum concept. So you get the number of flux quanta is total magnetic flux passing through the system divided by the flux quantum h over e. And then I will define a filling fraction nu e, which will be number of electrons by number of flux quanta. It basically tells me what fraction of these Landau levels are filled. Please do not confuse this nu e with the critical exponent nu. We often use the same symbol for various things in quantum Hall. There is one important property here of the Landau level. It's not just degenerate, it also has a topological invariant. So if I fill the lowest Landau level, I will get a topological invariant, the Chern number equal to 1. Each Landau level has Chern number 1. So, and this topological invariant will give some robust properties, like when we add disorder, there will be some effects due to this topological invariant. So what is quantum about quantum Hall effect? So in the 80s, early 80s, experiments were done on this system. So experimentalists were measuring the resistivity of this two-dimensional electron gas, and how it is done. You apply a current, for example, here it is in the y direction, and then you measure the voltage both in the x direction and the y direction. And then we can define a Hall resistance to be the ratio of electric field in the x direction and the current in the y direction. Now, if I have translational invariance, then it can be shown that rho xy is inversely proportional to the filling fraction. Remember that this is a continuous number. I can change filling fraction because it is defined as number of electrons by number of flux quanta. I can change it by either changing number of electrons, or I can change the magnetic field. So this is a continuously tunable number in experiment. And it is inverse filling fraction times quantum of resistance, h over e square. So you would expect that if I change the magnetic field, resistance will behave continuously as a function of magnetic field. However, when this experiment was done, they found that that was not true. And one got very nice quantization at rho xy. So look at the red curves, which corresponded to roughly having integer filling fraction. So nu e was integer. So you have quantization at h over e square, h over 2e square, h over 3e square, and so on. So that means that translational invariance is not preserved in the experiment, and one needs to add a disorder. So that will be the story for later. Now, there is one more thing that was done, which was when experimentalists made cleaner samples. They didn't only observe quantization at integer values of filling fraction, but they also observed quantization at rational numbers like 1/3. So this is the plateau at 1/3, and this is 2/5, and so on. So you get quantization at simple rational filling fractions. That is the quantum Hall effect. So just consider, so it's usually it is sandwiched between two semiconductors. So you get two-dimensional electron gas, which is trapped at the interface between two semiconductors. So they are free to, it's a semiconductor, so they cannot move in the direction perpendicular to the plane, but they are free to move in the two-dimensional plane. It's not a strongly interacting system. It will be a strongly interacting system. And studying those interactions, studying the effects of those interactions will be important later on in this talk. So the lattice scale happens to be very small compared to the length scale, which is important here. The length scale that's important here will be the magnetic length, which will be around 10 nanometers, 5 to 10 nanometers. So that will be bigger than the lattice scale. So for the purpose of this talk, I'm going to define nu e prime, which will be a quantized number. So it will correspond to the value of Hall conductivity at these plateaus. And nu e, I will keep that to be a continuous number. So this labels the state, this labels the charge, electron density, and so on. So crucially, disorder was invoked to explain this quantization because that's the obvious way to break translational symmetry.
At some very low temperature, right? At high temperatures, you probably just see a straight line.
High temperatures, yes. So this straight
So-
line can be understood roughly as the dimensionless temperature being
Yeah. So what is the temperature scale at which we would see this plateaus?
I think you can see it at hundreds of millikelvins. I don't exactly remember, but so what happens usually when you lower the temperature is that these transitions become sharper and sharper. So here it is a transition between nu equal to 1 and nu equal to 2. This becomes sharper and sharper as you lower the temperature. But you can imagine that if I have high temperature, this plateau will become very small. Will have a very small width. So it will become more like a continuous one, like you mentioned.
But roughly at what is the temperature scale where I would, in an experiment, I would expect to see this?
I think it's hundreds of millikelvins, somewhere around that. I might be wrong, but I think it's few
and
hundred.
depends on the.
Below 1 Kelvin.
Okay, and also depends on whether you have impurities and so on. Is it? I mean, is it better to have a pure sample or is it better to have a dirty sample?
So it's better to have some intermediate disorder. You have too strong disorder, you only have insulators, no quantum Hall phases. So if you reduce disorder, make it cleaner, then you get nice plateaus. And then if you make the sample even cleaner, you get plateaus at 1/3 filling fraction and so on. So we expect that as you make sample cleaner and cleaner, we will get more and more quantum Hall states. If you want to see this, you should be at intermediate disorder. Yeah.
What is exactly the green curve in the upper plot?
Thanks. So that is rho XX. So that is the one. An insulator, it doesn't dissipate energy at the plateaus, but at the critical point, that's where, so this is the critical point between two quantum Hall states, and you get some finite dissipative conductivity there, or dissipative resistivity. And this will be part of the later. Yes.
Yeah, quick question. So I guess when you talk about disorder, this is disorder in the scalar potential.
Yes.
Do most of these things go over if there is disorder in the vector potential?
Yes. So the crucial point here is that there is a topology in the Landau level. So they have a Chern number. Whatever disorder you put in, as long as it is not too strong, it won't break the topology. And it's not a symmetry protected state. So that's nice. It can survive all sorts of symmetry breakings. Okay, so I will be interested in the region here where this transition takes place, somewhere here. And now I'm going to tell you about what is the standard story of that and why it is inadequate, and also what we have done to improve the theory. So to understand the quantum Hall transition so we can start from a non-interacting electron picture and understand the quantum Hall transition. So let's start with the Hamiltonian p square over 2m. So curl of capital A is the external magnetic field, and add a random scalar chemical potential as the disorder part. We want to study nu e prime 1 to 0 transition. So we can project to the lowest Landau level if the spacing between Landau levels is large. So I'm going to consider omega c to be infinity. So I can project to the lowest Landau level. So if I had clean system, then this would be just a Dirac delta function in the density of states. This is density of states versus energy. But now, because I added disorder, I will have some regions which will have attractive chemical potential. So they will be lower in energy somewhere here. And I will have some repulsive regions which will be high energy, so that they will be here. So the Landau level degeneracy breaks due to disorder. Suppose my chemical potential, which determines how many electrons are filled, was above this density of states, then I just fill the lowest Landau level completely, and that will be a totally uniform state. Uniform in the sense the density will be uniform. But now in the presence of disorder, let's deplete this Landau level by a little bit. So I'm going to remove electrons somewhere from here. So what happens in this case is that single particle electron wave functions, they lie along the equipotentials of the potential.
I have a question. I guess you would try to motivate that it's a continuous phase transition.
Yes.
So what is the most compelling evidence from experiments that it is a continuous phase transition?
So this plateau width,
yeah,
this becomes sharper and sharper as you lower the temperature.
So that would mean that at zero, it's just a zero width. And
yes,
why should I not think about this as a discontinuous phase transition like a first order?
There will be a localization length that will diverge.
I see.
The
So there, that's where the scaling is.
Exactly.
Okay.
Exactly. So that's where the scaling comes from. You can try doing.
Wait, sorry. Question on Zoom. Which is the plateau width that you're saying will shrink to 0? I didn't follow that comment.
So this transition width from here to here, this transition width, or you can look
Actually,
at.
I can't see your cursor when you move it on the, when you point, I can't see the pointer. So I don't know which one.
I see. So this transition width here.
Oh, I see. Okay.
Or this row axis, this width of the row axis. That will
Yes.
shrink to 0.
I see. But it's a continuous transition because there's a growing correlation.
Yes, exactly.
Okay. But the width of the plateau, how is that related to the disorder? You said that the disorder is crucial. So is there a sort of a simple relationship between the width of the plateau itself and the disorder, or no?
I think you will have to do numerics and derive it. I'm not sure if you can find it.
No, just at a qualitative level. If there's no disorder, there's no plateau, right? Or is there a plateau?
Right. If there's no disorder, there is no plateau. Yes.
And too much disorder kills everything.
Yes, but that is due to Landau level mixes.
Yes.
If I project to a Landau level,
Yes.
everything will survive, even at strong disorder.
Okay. All right.
I think things will become clear as I present this picture of the transition. So here, if I want to deplete electrons from the very high energies in the lowest Landau level, then single particle electron wave functions, they lie along equipotentials of the scalar potential V of R. So you can imagine that I need to remove very high energy regions. I need to remove electrons from very high energy regions in the sample. So what it will do, it will create these holes in the two-dimensional electron gas. So I can understand them as nu E equal to 0 regions and nu E equal to 1 regions coexisting. And because this is very high energy, these nu E equal to 0 regions are going to be localized. So these are going to be small regions in the sample. And further, there will be edge states moving when I go across nu E equal to 0 to nu E equal to 1. So that will be a chiral edge state. It's just the skipping cyclotron motion I described earlier. On the other side, when I have very small number of electrons, in that case, I will have regions of nu E equal to 1 that will be small, and regions of nu E equal to 0, the other color, that will be percolating throughout the system. So here, nu E equal to 1 percolates throughout the system. Here, nu E equal to 0 percolates throughout the system. If I look at the edge states, here there will be an edge state at the border of the sample, and I can label this state as nu E prime equal to 1. So this will be the integer quantum Hall state. This will create that plateau. And this will be an insulator without a Hall conductivity. And this will also have a plateau at 0 Hall conductivity. So somewhere between there will be a transition between the two. And at the transition, both nu E equal to 0 regions and both nu E equal to 1 region. So both regions will be extended throughout the system. And there will be these edge states extending throughout the system. They won't be like here. So here they are localized, and here they will be extended. So in terms of the density of states, what happens is that the density of states gets broadened by disorder. All of the states are localized. Most of the states are localized, except at one energy, at roughly at the middle of the Landau level. If you have some particle-host symmetry, you can argue it should be exactly in the middle of the Landau level. So we have these localized states all over, and one state is, so states at one energy are delocalized. And these are the states that lead to the non-zero Hall conductance. And why must they be present in the system is because if I had only localized states, by localized, I mean they are not affected by boundary conditions. They decay exponentially from their centers, for example. So they are spatially localized at some points. If I only had localized states, they cannot give me a Hall conductance. So somewhere, because the Landau level has a Chern number and a Hall conductance, that implies that somewhere in the band, there must be delocalized states. And here it exactly occurs in the middle because of some particle host symmetry. So near filling fraction 1/2, this will happen. Now the transition is obtained as I change my chemical potential. If I start here and reduce my chemical potential, as I cross this delocalized state, I will see that transition between two plateaus. And also the localization length will diverge as a function of as I approach this critical point in the middle.
One question. In this picture, how does the number of delocalized states in the band scale with the area of the sample?
So that's a very good question. Actually, this is related to Ravin's work from the 2000s. It's a sub-extensive scaling. I don't exactly remember the exponent, but the number of states goes to 0 in the thermodynamic limit.
Number of states goes to 0 or density goes to 0?
Fraction goes to 0, yes.
Anyone who wants more about that, come to my talk.
Yeah, I have a quick question. So surely this picture cannot hold if V of R is white noise, right? Because if V of R is white noise, then you won't be able to make the statement that these puddles are locally quantum Hall-like.
So this is one situation, but people have done this with white noise. Roughly the picture holds. I mean, it ends up working. You get the same transition, and also Ravin has also done this model. You get the transition. Essentially, the idea is that you have a Chern number in the system, and that means somewhere there must be delocalized states. And people have tried many different models, and it's always one energy where you find delocalized states.
Yeah, but you don't need any separation of scales between the, say, the length scale over which your random potential varies and the magnetic length, for example.
Yes, you don't really need it. Yes, but this is a nice picture. I'm going to move to in the next slide. I will show you an effective model using this picture. So
would it be correct to think of the delocalized state as the one on the boundary?
So here in this, they are actually delocalized all over the bulk. So you can think of this. So single particle states move along equipotentials in this case. So these are equipotentials. They are delocalized all over the bulk.
You see, so I should think of the union, that union of that boundary as the sort of the support of that wave function.
Yes. So now there was an effective model proposed by Chalker and Coddington, which said that most of the physics near this transition takes place near the saddle points. These are saddle points in the potential, where two lakes, the cyan color, or the two islands come close to each other, and the edge states scatter off these nodes. So what they did was they arranged these nodes in a uniform lattice, and then considered the propagation of edge modes between nodes, and they scatter in some specific ways around these nodes. So for example, let's take this particular case. There are edge states moving between this. There's an edge state moving between this node and this node. And if this scatters down, then this will give me nu e prime equal to 1 state. And this can be seen as follows. This is a boundary between vacuum and the quantum Hall system. And you can see that there's an edge mode moving at the edge. Similarly, there's a chiral edge mode moving at the other boundary. However, if this edge state scatters up instead of scattering down, in that case, you can see there is no chiral edge mode near the boundary. So that's nu e prime equal to 0. And you can get this transition by continuously tuning the scattering from down to up and get a critical exponent.
One question about the transition from the previous picture to this regular picture. In the previous quantum percolation picture, you are imagining these little bubbles of cyan inside the other color. And, you know, in usual percolation problems, these holes inside other things, they can have interesting fractal structure to their boundary, right? So the total boundary, if you count internal boundaries, often scales with some non-trivial dimension. But you've lost all that in the next slide where you just made a regular array.
Exactly. Yes.
So what is the argument to say that there isn't any non-trivial fractal exponent of these boundaries that contributes to the actual transitions character?
So if you consider those saddle points, the fractal structure, that will lead to the classical percolation problem, which has been solved, and you get an exponent of 4/3. Here, we want to consider the quantum percolation problem.
Right, but I'm saying in the quantum percolation problem also,
Yes.
this is related to Rajesh's question. He was saying we should look at the union of all boundaries, and I thought you agreed with him.
Right.
Now,
So
that union of all boundaries, if you want to define a quantum problem on that, that can already have an interesting geometry that you need to take into account. That is taken care of by something else.
yeah, so let me explain what the background here is. So first it was done on a regular lattice, and people found some exponents. This has nice scaling when you do the correlation length scaling. People later generalized it to include those effects as well. So one thing you can do is you can make these scatterings random at the saddle points. You can also, that was shown to be irrelevant in the 90s by Steve Kivers and Doug Hiley. So that's one thing. More recently, people have done what you are asking. Can I make geometric disorder? Can I have fractal structure? People have done that, and the story becomes very complicated. Exponents, you get a lot of irrelevant scaling. So there are too many parameters, and it's hard to do scaling. So people have done it, but yeah, maybe that's a remaining question you can say.
I think there is a related question by Rasdeep, whose audio is not working. So the question is that Coulomb interactions would presumably control the scale of the puddles. How good is the non-interacting picture in drawing this?
I will explain to you that it is not good.
Okay.
So that's part of my.
Okay. Yeah.
Thanks.
Can you please explain this once? This picture.
Yes. So you have, suppose this is an edge state. So there is a phase. There is a single particle which moves from this point to this point, and then the single particle wave function has some amplitude of going down and some amplitude of going up. So this is a situation where you have just the amplitude of going down. And then if you look at the boundary, you will get, if you just follow this type of scattering on all the puddles, you will get this chiral edge state.
I mean, that seemed like a edge state even in the bottom picture. Or am I?
But yeah, it's not moving chirally, so it's not moving.
Oh
in,
no!
actually
But on the
going...
top, on the top, it seemed like is it, yeah.
So it's actually also localized.
It's localized and it scatters in that.
Yes. Yeah. So actually, yeah, the color inside the saddle points, that's determining the scattering. Yeah.
Oh, I see.
Yeah. So now this problem has been studied quite a lot, and we have, I think recently we have the best estimate of the exponent of this transition in the Chalker-Coddington model, the network model, and it turns out to be nu equals 2.61 roughly. Moreover, we also have, in addition to correlation length exponent, we also have dynamical exponent. So we have the dynamical exponent roughly can be defined as the scaling between temporal component and the spatial, the temporal correlation length and the spatial correlation length. And here, there's one property that the density of states is finite, and that is the only, let's say, the dimension-full quantity. And density of states in 2 dimensions scales as time over length square. So this will give rise to z equal to 2 scaling in the at the transition. And this should remind you of diffusion equation. Diffusion equation is first order in time, second order in space. So this gives rise to diffusion at the critical point. Away from the critical point, you have localization. So you cannot go to long distances, but at the critical point, you can travel long distances. However, when the experiments were done in this in the 2-dimensional electron gas, they found that the exponent nu times z, so product of these, was 2.38. So that's significantly different from 5.2, what you will get here. Moreover, dynamical scaling, which is somewhat controversial, many people would say that dynamical scaling has never been measured in the experiment, but it seems that dynamical scaling in many experiments is close to 1, as opposed to close to 2. So if I were to say, let's divide nu z by z, then I will have a 10% difference with nu. So it seems that the experiments in theory don't match. There's a significant difference, and interaction effects have been invoked, thought to be the reason behind behind the breakdown of the single particle picture of the integer quantum Hall transition. Yes.
Quick question. Am I audible?
Okay, so even before you invoke interaction effects, I mean, presumably at the critical point, the states are multifractal or at least fractal.
Yes.
So is there any sort of compelling reason to expect that it will be diffusive and not subdiffusive? So I mean, naively, I would have expected the dynamical exponent to correspond to subdiffusion and not diffusion, just because the states are multifractal.
You can measure this in numerics. You can measure conductivity in the numerics and density of states. It turns out to have z equal to 2 scaling, so it's diffusive. Conductivity is finite at the critical point.
How do I understand that? But I also know that numerically I do get multifractal states at the transition.
I think in one dimension that's probably more important. But in two dimensions, you can just measure conductivity and scale it with system size. And as system size goes to infinity, conductivity stays finite.
Yeah, Srijit, please go on.
Okay.
Hi, I'm audible, right?
Yeah.
So if I remember correctly, the scaling exponents are calculated from the width of these plateau transitions. How do you get two numbers, nu and z, from resistance measurements?
So nu z?
Yeah, you get nu z and z separately. So how are they determined in the experiments?
So nu z can be just determined from looking at the width of the plateau transition regions,
right,
and then scale it with temperature. That gives nu z. Z can be done in different ways. Here I have referred to 3 different experiments. So you can look at nonlinear scaling between current and voltage. You can look at microwave conductivity, and also you can look at some system size temperature scalings. So they are done in different ways, but each of them is controversial in its own way. So we can say there are some doubts, but so far I would, for the purpose of this talk, I will just take z equal to 1.
Cool, thanks.
So that's one problem, but there is even more interesting issue with the non-interacting transition, which is that there are not just transitions between integer quantum Hall and insulating phases, but there are also transitions between fractional quantum Hall phases. So for example, here I have a plateau transition between 1/3 state and 2/5 state. And the exponent nu z has been measured at this transition, and it's 2.33 in the experiment, which is close to the 2.38 in the integer quantum Hall transition. Moreover, I can measure the dissipative rho xx resistance at the critical point. It turns out that for 1/3 to 0 transition and 1 to 0 transition, so the open circles here are 1 to 0 transition and the filled circles are 1/3 to 0, the critical resistance appears to be very close to h over e square in both cases. So this was a conjecture which was made in the 90s around the time when I was born, that quantum Hall transitions are super universal. By super universal, we mean fractional transitions and integer transitions are in the same universality class. And since then, it has remained a conjecture. So we have a confluence of topology, disorder, and interactions. Experimental observations are very simple. They are compelling. However, there is a problem in the theory, which is that integer quantum Hall effect and fractional quantum Hall effect are studied in different ways. One is studied purely from the non-interacting perspective. The other one is studied starting from interactions, and it is very hard to do. So we need a unifying framework to study everything in one picture. So what is that? What could that unifying framework be? There is already a unifying framework for studying fractional quantum Hall states and not the transitions. So what we have done is extended that framework to study the transitions and then argued for the emergence of superuniversality and the right dynamical scaling. So the unifying framework is called composite-fermions. And what they do is they map fractional quantum Hall states to integer quantum Hall states. So then we can study everything in one picture. So here is what a composite-fermion is. It is electron bound to 2 flux quanta or 2 vortices. And let's see how it maps fractional quantum Hall states to integer quantum Hall states. Here I have 1/3 filling fraction. So I have 3 flux quanta per electron. And I can combine 2 of them with the electron to form a composite-fermion. So I will have one flux quantum and one composite fermion, and that will be filling fraction 1 of composite fermion. So we need to distinguish between filling fraction of electrons and filling fraction of composite fermions. So we have mapped 1/3 the fractional quantum Hall state to an integer quantum Hall state of composite fermions. Similarly, we can map the 2/5 state to filling fraction 2 of composite fermions, again an integer quantum Hall state. We can map the entire fractional quantum Hall state filling fractions p over 2p plus 1 to these integer quantum Hall states. Let me show you something more trivial, which will be important in a minute. The nu E equal to 1 integer quantum Hall state of electrons can also be mapped to an integer quantum Hall state in composite fermions. So here I have an overall 1 flux quantum per electron, attach 2 of them to the electron to convert it into a composite fermion. What happens is that the flux quantum just reverses sign. So that I will call that as filling fraction -1 of composite fermions. There is one more thing that happens at half filling. So here I have 2 external flux quanta per electron. If I combine them with composite fermion, I don't have any magnetic field left over. So this composite fermion will feel no magnetic field, and it is at finite density. So it will form a Fermi surface. And this will be the topic of my seminar tomorrow, probing the non-Fermi liquid nature of this composite fermion Fermi surface. In this talk, we are interested in the plateau transitions. So we need to figure out how to add disorder to this picture and get the transition. Yes.
What about 3/5? What if you have 3/5 there? Do we not have like remaining electron? I mean,
so at 3/5, what we have to do is first do a particle hole transformation that converts 3/5 to a 2/5 of holes as opposed to electrons, and then do this picture.
You say that transition in fractional and integer belongs to same universality class.
Later on, I will show in the theory how it can happen.
Yeah, so my question is, then is it correct to claim that interaction is not essential to understand the transitions for fractional, or it doesn't play any role to understand the transition because integer quantum Hall is also involved, right?
Yes, so it will be. So that's a very nice question. So here, at this point, I have considered that the role of interactions is to bind flux quanta to electrons, to convert them to composite fermions. So this can be done by having repulsive electron-electron interactions. These vortices have depletion of charge density near their center. So they like to bind with electrons. And this process will minimize short distance part of the interaction. What will happen is that the long distance part of the interaction will also matter. And that has not been taken into account here yet. And I will explain what that does. Yeah, thanks. That's a very nice question. Okay, so now how do we reformulate the quantum Hall transition in this composite fermion picture? I will explain some equation and I will derive a Hamiltonian, and then I will show you that this Hamiltonian, many of its properties can be solved just analytically.
Can I ask a question?
Yes.
So this a few words of justification.
So the Laughlin wave function roughly has, at the 1/3 filling fraction, Laughlin wave function has 3 flux quanta bound to each electron. So you get, so the essential part is that microscopically you are lowering the energy because vortices have some depletion of charge density. So that likes to be near electrons. So here you bind two vortices to electrons to convert them to composite fermion. Laughlin state has 3. So what happens is that because this is a composite fermion, we'll have a Slater determinant that will give you an extra vortex bound at each electron. So it's just minimizing energy. Yeah, there was in the 80s, it was thought that it would be a Wigner crystal, which minimizes long distance part of energy, but turned out that Laughlin wave function had just like 1% lower energy than the Wigner crystal, and for Coulomb interactions. So that, yeah, it's energetics maybe. Yeah, in other Landau levels, you can get those crystal states. So now I'm going to use a Dirac. So for this composite fermion, now I'm going to transition to a field theory and derive a Hamiltonian. Let me just give you the main aspects of this. I'm going to use fermionic version of particle vortex duality. It was initially proposed by Son and then later on interpreted in this way. So here I'm going to use the Dirac fermion version. So I'm going to consider Dirac electrons here on the left side. So I have Dirac electrons in their 0th Landau level. And this has no distinction compared to the p square over 2m electrons I have been talking about until now. When you project to the Landau level, everything looks the same. That can be dualized to a composite fermion, little psi, which is also a Dirac composite fermion. It will interact with an emergent 2+1 dimensional gauge field. This is a dynamical gauge field. And there will be this external vector potential, which just comes from this left side. We have magnetic field, etc. We want to probe this with electric fields and so on. There are two important equations that we need to know, which is that the composite fermions are at finite density. So their density is external magnetic field by 4 pi. 4 pi is just 2 flux quanta. This relates to the flux attachment. The second equation says that the electron density, which you probe in an experiment, so that will be capital B minus little b. Little b is the magnetic field of this little a, the emergent magnetic field, by 4 pi, again 2 flux quantum. And again, at half filling, you can see this rho e will cancel this capital B, and we will have on average little b to be 0. So the previous is just the previous slide now converted into equations. So now my philosophy will be, okay, by binding these fluxes, we have already taken some interaction effects into account. So let's first assume that this emergent gauge field does not fluctuate and do a mean field theory. So that's what my assumption will be, and I will write down a mean field non-interacting. So the composite fermions will be non-interacting, and I will write down a Hamiltonian for them. So to motivate this Hamiltonian, because I have a scalar electric potential for the electrons, that will give rise to fluctuations of electron density. So remember those puddles, you had holes, nu equal to 0 regions and nu equal to 1 regions. So it will give rise to a spatially varying electron density. And from this equation, you can see, because capital B is fixed, this will give rise to a spatially varying little b, or a random magnetic field for the Dirac composite fermion. So this motivates a Hamiltonian like this. I have Dirac fermion sigma dot p. Sigma is just the Pauli matrix, and little a that corresponds to this, but I'm going to consider it to be fixed in space. And I will have a chemical potential because composite fermions are at finite density. So curl of little a is the magnetic field, emergent magnetic field, and I'm going to divide it into two parts. So this will be useful in the next slide. I will have a uniform piece, little b naught, and I will have a random piece. So the spatial average of this is 0, and this will be a tuning parameter, b naught. So to understand this b naught, just look at this equation. If I change the average value of p, I'm changing rho e, the density. And remember, filling fraction is rho e by density of fluxes. So I'm changing filling fraction by changing b naught. So b naught will be a tuning parameter. It will take me from nu e less than a half to bigger than a half. And b tilde will be the disorder part, the random piece. This will be a spinner. Yeah, it's a spinner. It's not a real physical spin. Understanding how they actually emerge from microscopic theory is still an unsolved problem. Yeah, thanks. I'm considering spin polarized electrons. So yeah, thanks. Now, a very nice thing about Dirac fermions is that their behavior in this random magnetic field problem will be fixed by three things. One is 0 modes. There will be a parity anomaly. And also, due to disorder, there will be Anderson localization or localized states in the system. Let's look at each of these three things, and that will give us the picture. So let's first look at 0 modes. So what are these 0 modes? This is the Dirac Hamiltonian written using complex coordinate z equals x plus iy. And a 0 mode wave function, for example, looks like this. The first component, so this is Dirac composite fermion wave function. The first component is 0. The second component is non-zero. And if this piece annihilates this, then you get a 0 mode. And what is the property of this 0 mode? the number of these zero energy modes is given by number of emergent flux quanta passing through the system. So they are exactly here at the zero energy, and that's their number. So if I was at B naught less than 0, which corresponds to filling fraction above a half, I will have some zero modes. If I was here, again, I will have some zero modes for filling fraction less than a half and B naught bigger than 0. However, right at the transition where B naught is 0, I will have no zero modes, because the number of zero modes is number of emergent flux quanta. There is one more property, which is that these zero modes are exactly like a Landau level. So they have some Hall conductance. And for Dirac fermions, we can show that the zero modes by themselves have a Hall conductance minus E square over 2h. In this particular case, nu E bigger than a half, and E square over 2h here. And because here there are no zero modes, you have zero Hall conductance coming from these zero modes. So that's the first component. The second component is parity anomaly.
The mu CF parameter, the composite fermion mu.
Yes.
Does it get determined by the previous parameters, or I mean?
Yeah. So mu CF is determined by the density. Density of composite fermions is B over 4 pi. That will determine your. Important thing is that this is positive, so it's not at 0. So now the second is parity anomaly. Single Dirac fermion is not invariant under gauge transformations in 2+1 dimensions. So the way to fix this, to preserve gauge transformation, is introduce a second Dirac fermion, a partner Dirac fermion, which can have a big mass. So here is the density of states of a massive Dirac fermion, and my chemical potential will be here. So the massive Dirac fermion will not affect my low energy physics at all. And I can take this mass, capital M, to be infinity. And effectively what this does, it shifts the Hall conductivity by minus E square over 2h. So the story of previous slide now transforms into this. If B naught is less than 0, remember this is filling fraction bigger than a half, I will have minus E square over h Hall conductance. For B naught bigger than 0, I will have 0 Hall conductance from 0 modes. And right at the critical point, I will have minus E square over 2h Hall conductance.
Can you explain the first two lines? First two lines.
Yeah, so this says that if I take a single Dirac fermion and compute the partition function of that, for example, in Euclidean time, under large gauge transformation. So large gauge transformation, for example, you can consider a cylinder geometry and then thread a flux through the axis of the cylinder. And if I thread one quantum of flux, the partition function changes sign. And that's not physical. So what you do is add a second Dirac fermion, which will cancel the sign. But we want to not affect, we want to keep we don't want to affect the low energy physics. So what we do is add a mass to that partner and take the mass to infinity. So that's the second component which shifts the Hall conductivity. So these now might look more familiar. It's minus E square over h and 0. Now the third is now add disorder, and let's see what happens. Generally, when we add disorder, single particle states get localized in 2 dimensions. However, that ignores topology, the Chern number. So we use the Laughlin gauge argument, which takes into account the topology. It says that if the states are localized at the Fermi level, then the Hall conductance is integer times E square over h. And we are going to also use the contrapositive. If the Hall conductance is not integer times E square over h, states at the Fermi level are not localized in that case. So let's see, in this situation, for B naught less than 0 or filling fraction bigger than a half, the Dirac composite fermion will have some 0 modes, but all positive energy states will be localized. So if I put my chemical potential here, I'm going to just get the Hall conductance from these 0 modes, and that will be minus E square over h. Similarly, on the other side, I'm going to get 0 Hall conductance, again from the 0 mode plus the massive partner. Again, all states will be localized. However, something interesting happens right at the transition where the Hall conductance is minus E square over h, minus E square over 2h, which is not integer. So this means that at the Fermi level, the states cannot be localized. They are all extended. My argument did not depend on where I put the Fermi energy. So all the states throughout the spectrum are delocalized in this case. So what will happen as I tune my B naught from here to here, and I have some Fermi energy here, then the localization length is going to diverge as I approach this critical point at B not equal to 0. And that will be now a transition. So we have translated the transition, which was in terms of non-interacting electrons, to composite fermions. And because of this Laughlin gauge argument, this quantum critical point is going to be robust to interactions, at least weak interactions, as long as I don't break this theory completely. Yes.
When you add disordered, the rho of E continues to look like this, even away from zero modes. You still have that linearish dispersion going into the semi-metal-like dispersion. Yeah.
So actually, I know what happens here. I don't really know what's this actually. I just drew it like that. But here at this zero energy, it is known that you have power law density of states.
But it's not linear.
It's not linear. It's faster than linear. But actually here, I don't know the answer for average magnetic field.
Okay.
But thanks for that question. And this is known to be a conformal field theory, and you can understand many of its properties. Yes. Now, using this picture, I have translated filling fraction 1 to 0 transition in terms of composite fermion minus 1 to 0 transition. This is still an integer quantum Hall transition. So now here comes the power of this theory. We can also translate fractional transitions into the same theory. So how do we do that? Take the 1/3 to 0 transition, first attach 2 flux quanta, and this will map it into 1 to 0 transition first. So remember, 1/3 state goes into filling fraction 1 of some intermediate composite fermion. Now this side looks exactly like this. So we can attach two more flux quanta, do this procedure, and now obtain -1 to 0 transition for the 1/3 to 0 transition. So overall, we need to attach 4 flux quanta to obtain a fractional transition. But because it's the same composite fermion theory, you will get you expect to have the same, at least at the mean field level system theory.
Srijit, just go on.
Right. So in the actual experiments, the transitions are usually not from 1/3 to 2/5. There are intermediate states where the flux attached changes rather than the number of lambda level changing. So is it possible to consider transitions where the number of fluxes attached changes rather than the n changing, mu CF changing?
In general, you can do that. So you can study any fractional quantum, any abelian fractional quantum Hall transitions. So what you have to tune, you can change 2 things. One is number of flux quanta. And the other thing is number of inert Landau levels. You can add some inert Landau levels which don't change the physics, and then you can study.
I was saying it's not the transition may not be from 1/3 to 2/5, but it could be from 1/3 to some intermediate state. Okay, I don't remember what fraction, but say 3/7 or something.
So if those, I think those transitions will not be covered in this theory. So the transitions where Landau levels in some composite fermion language, there's a change of only 1 Landau level. Only those transitions will be covered by this theory.
Okay.
Sorry, can you just explain the second and the third line? I didn't follow.
These 2 lines?
Yeah, these 2 lines.
So if I attach 2 flux quanta to this theory, 1/3 state maps to filling fraction 1, and this maps to 0, yeah. Then this becomes identical to this.
Sure.
So this is the lowest Landau level of the intermediate composite fermion. And then I can just again play this game, attach 2 more flux quanta, and then this will become the Dirac fermion in zero magnetic field.
I see.
And then, yeah.
Okay.
So far, I have only done mean field theory for composite fermions.
Sorry, you're assuming that there is this hierarchy of Dirac composite fermion theories, which
Yes.
works, and you just add flux quanta.
Exactly.
Okay.
So far, I have only considered short distance parts of interactions which attach flux quanta, and I get some mean field theory description of quantum Hall transitions, both for fractional and integer. Now, as I alluded to before, you need interaction effects. For example, Coulomb interactions for z equal to 1. So to now study interaction effects, we add this Coulomb interaction. So this is just density-density interaction with interaction potential V of Q. And if V of Q is 1 over Q, that is 1 over R interaction in two dimensions. And if V of Q is U0 constant, then that's a short range. You can take that to be a Dirac delta function type contact interaction. So now remember that rho of E in the composite fermion theory, rho of E is related to emergent magnetic field little b over 4 pi. So I can convert this into a flux-flux interaction in terms of composite fermions. One more thing, I will use transverse gauge. So little b of Q can be written as Q times A transverse of Q. And this will be just Q square VQ times A transverse square. So this is my interaction term. And I will show you now that this will lead to the correct dynamical scaling and also will lead to super universality using some very generic arguments. So let's first see how one can get the right dynamical scaling. So let's now consider effective response of composite fermions. They have some finite conductivity. Effectively, that can be understood by integrating out composite fermions, and that generates this term, sigma xx of composite fermions times omega, and this is mod AT square. And the second term is just the interaction term from the previous slide. Now, if V of Q is 1 over Q, you can see omega will scale linearly with Q. So you can get Z equal to 1 Coulomb, Z equal to 1 scaling with Coulomb interactions as long as the sigma xx is finite at the transition. And
do you actually derive this, or it's just possible?
So you can make this argument. The thing is here is that this is very general based on expectations, but you can also derive this using nonlinear sigma models and integrate out diffusive modes from the nonlinear sigma models and find this term.
There's a calculation.
There is a calculation you can do, but that suffers from issues like it is valid only at large sigma xx. But we want to make general arguments for the critical point. Yeah.
So when you map fractional quantum Hall state to integer quantum Hall through this composite fermion,
Right.
You get integer level, right? So what happens to the first energy excitations in these two pictures?
That's a very nice question, actually.
How does that? Yeah.
Yeah. So let me tell you what happens. And that's also something we resolve in a sense.
Okay.
So I have to go back many slides. Let's see. So let me come here. Yeah. Suppose you were, suppose because critical point is here, let's put our chemical potential here and then look at the excitations, right? So if I move an electron from here to here, you can see I'm moving an electron from a localized state to another localized state, right? So the excitations here seem to be localized. But then you can ask the question, how do localized excitations will lead to a finite conductivity? Conductivities come from excited states, right? The dissipative one, you have to transition to excited states. So that was also an issue with the non-interacting picture. However, it was argued that in the non-interacting picture, if you add some interactions, like add just irrelevant short-range interactions, that will fix this issue. Excitations will become delocalized in that case. But in our picture, the composite fermion picture, this is obtained just at the mean field level. You see, this is the critical point in our picture. And throughout the spectrum, we had delocalized states because of anomaly. So if I put my chemical potential here and I create particle-hole pairs, they will be delocalized. So you will get finite conductivity at the mean field level, at the non-interacting level by itself. You don't need to add any interact. Yeah.
Maybe I'll talk to you later also.
Yes.
So in this picture, the sort of mobility edge sits at 0 all the way to the critical point and then immediately diverges. So you have extremely close to the phase transition on either side.
Yes.
all the states apart from the zero energy states are strictly localized,
Right.
and all of them
All of them,
diverge at the
yes,
same point.
yes.
I see.
People have
Okay.
studied these numerically as well.
Uh-huh.
You see this.
I see.
Yes.
Okay.
By the way, at the topological insulator surface, you get single Dirac fermions.
Yeah.
And they cannot be localized by impurities.
Sure.
So it's the same thing.
Yeah.
Yes. At zero at this point. So with this generic assumption, you will find a z equal to 1 scaling, omega goes like q, and this can be understood physically. Suppose I had no interactions, then I consider a charge density fluctuation. The charge density without interaction just relaxes by random walk, so that leads to diffusion, z equal to 2 scaling. However, because we have Coulomb repulsion, due to this term, this charge density will also feel an outward repulsion because of that. And this leads to super diffusive relaxation, or z equal to 1 scaling at the critical point. So that's the intuitive picture. A second interaction effect will be super universality. That means fractional transitions and integer transitions are in the same universality class. So how do we see that? So we add this term, the Chern-Simons term. So it has two gauge field, the gauge field little a. So you have the temporal component of the gauge field and the transverse component of the gauge field. You have a cross term, and this capital lambda basically controls, so this little lambda controls how many flux quanta I am attaching. Remember that for fractional transitions, I needed to attach 4 flux quanta. For integer transition, just 2 flux quanta. So this lambda, by changing this lambda, we can control that. And this is the only difference in the theory of the two types of transitions. So if we can show that this term is irrelevant, then we can get super universality. And this can be actually seen. So because composite fermions are at the transition, are at the critical point, they have a finite density of states, they will screen. And this second term is the Debye screening coming from composite fermions. NF is the density of states at the Fermi level. And this third term is basically what I had in the previous slide. So here I can integrate out little a tau. And what will happen, I will get this effective Lagrangian. So you can see the lambda dependence is only in the first term, and it goes like q square. And the second term is the interaction. And again, if the interaction goes like 1 over q, like for Coulomb, this term will be more important than the lambda term. So this way we can see that this lambda is irrelevant if I have Coulomb interactions. And this only requires this assumption that the density of states is finite at the Fermi level. Notice one thing, if I had short-range interactions, V of Q is a constant, then both of these terms are equally important. And we do not know that for short-range interactions, if the super universality will hold. So if new experiments are done with screened Coulomb interactions, there it might be very interesting to see if you get the same exponents for integer transitions and fractional transitions. And so far, we cannot say anything about that situation. But for Coulomb, you get super universality with a very general assumption. So these are the two main conclusions. We have robust interaction effects, which say that you will get identical exponents for integer quantum Hall and fractional quantum Hall transitions. You will get dynamical scaling z equal to 1. Moreover, we also tried to compute the localization length exponent nu for this composite fermion theory. So we have so far done it only at mean field level. And we found 2.56. So it does not match with the experiment either, the 2.38 value. So we think that this is some problem with the mean field approach. So we want to extend in future, we want to extend this mean field approach and add the gauge fluctuation interaction effects that I mentioned before. So our one direction is to understand those interaction effects at Hartree-Fock level. It's a 4 fermion interaction when you integrate out the emergent gauge field, and that 4 fermion interaction can be studied within a Hartree-Fock approach. And it should help us improve our critical exponent and see if that matches with the experimental value. Moreover, to understand the z equal to 1 scaling that I derived here from very general expectation, we can study relaxations of charge density using some time-dependent numerical techniques like time-dependent DMRG and see if one gets that z equal to 1 scaling for Coulomb interactions. and Z equal to 2 scaling for short range interactions. I'm also motivated by this general question, is dissipation universal at quantum Hall transition? For example, some experiments see that the critical resistivity rho xx, that appears to be universal at the transition. How about thermal conductance? Will that satisfy Wiedemann-Franz law, etc., in this composite fermion theory? So that's the first part of my talk. And I don't know how much time do I have?
Okay, so what do you think? How much would
I
you
can give a brief overview in like 5 or 10 minutes.
15 minutes? Yeah.
Okay. Yeah, I think 5 or 10 minutes should be sufficient. Sure. Yes. So let's see. So the first part of this talk was about disorder, topology, and interactions. And this second talk will be about, we will consider a clean system, no impurities. So we will have now an interplay of topology, interactions, and spontaneous symmetry breaking. So what I will show you is some numerical evidence for a transition from a fractional quantum Hall state, which is a strongly interacting topological state, to a conventional symmetry breaking, spontaneous symmetry breaking state, the striped state, which will break a translational symmetry. So, and this is, as I mentioned before, this is a work done with Ravin, who is present in the audience. So we are motivated by this general question: could there be a continuous transition between a topological state and a conventional Landau spontaneous symmetry breaking state? And our motivation comes from an experiment which was done on this 2-dimensional electron gas. So what this experiment did was they considered the first Landau level, not the 0th or the second or the higher Landau levels. So they were looking at 1/3 filling fraction of the first Landau level. You get the Laughlin fractional quantum Hall state usually. And then what they did was they tilted the magnetic field in the plane of the 2-dimensional electron gas. So what it does, it introduces anisotropy. And you can tune that anisotropy because you can tilt the magnetic field as much as you want. So what they found was that the resistance, they measured resistance in the x direction and the y direction. This is the longitudinal resistance. And they show very different behaviors at low temperatures. So this y resistance, RYY, it goes to 0 at 0 temperature, and RXX, it seems to go to some either finite value or diverge at the low temperature. And what the experimentalists proposed was that this was due to a transition from Laughlin type fractional quantum Hall state to a spontaneous translational symmetry breaking state. So this is density, electron charge density, and you can see it has a modulation, and it is a very anisotropic state. And so our question was, we do not know whether this transition, first, does it occur? And second, is it continuous or is it first order? And I will show you evidence that this is a continuous transition. So to begin with, why does this happen in the first Landau level? So the reason is that if you look at the 0th Landau level, you get very robust fractional quantum Hall states. They have large gaps. It's hard to destroy them. In the second or higher Landau levels, you get spontaneous translational symmetry breaking states or spontaneous rotation symmetry breaking states. Those are the standard Landau type transitions or Landau type states. N equal to 1 Landau level is intermediate, where fractional quantum Hall states have small gaps, so you can destroy them by changing some parameter and obtain some transition. And this is exactly what we found. So let me briefly mention that we use this technique called IDMRG and introduce anisotropy in the system in the first Landau level. We are projecting to the first Landau level, and we are studying the phase diagram as a function of the anisotropy. And here is a scaling plot. So here we have 3 quantities in the plot. One is inverse correlation length. It is the red curve. We have some measure of the gap, energy gap. So that's the green curve. And this blue curve is the Fourier component of density. So we do obtain some transition to a spontaneous symmetry breaking state. And you can see then when we fit these 3 quantities to power laws, the fitted curves all meet at one point. And this shows very nice critical scaling as a function of the anisotropy alpha. Alpha equal to 1 is isotropic. So we don't actually have to add too much anisotropy to get this transition, at least at this particular size. So this is an evidence for a continuous transition from a fractional quantum Hall state, which is on the left side, and a spontaneous translational symmetry breaking state on the right side. We also measured the period of this stripe state, and it was around 5.4 magnetic lengths. So that's an experimental prediction. And if someone can figure that out in an experiment, they can compare with our value. So besides this particular case, there are other possibilities which have been predicted by experiments for these transitions. For example, there was an experiment maybe in the last 10 years which applied pressure to the two-dimensional electron gas. And what they found, so if you apply pressure, it is isotropic. You're not introducing anisotropy. But what they found was that as they increased pressure, you started with some isotropic state. So the green curves and the red curves here at this point, 5½ in the middle of this plot, that's the X. So green curve, I think, is the X resistance, and the red curve is the resistance in the Y direction. So as they increased pressure, again, they saw some nematic state or rotation symmetry breaking occurring at some finite value of pressure. So we do not know whether this is a transition to a nematic state, or this is a transition to a stripe state, or if this is a continuous transition, or it is a first order transition. So this will be a very nice thing to study using numerics. And I think this is very appropriate to use here. It is very appropriate to use that IDMRG I mentioned. There are further examples of these transitions. For example, at even denominator filling fractions, 1/2 and 1/4, people have changed the nature of interactions by considering wide quantum wells and so on. They also see a transition from a Fermi surface to some non-abelian fractional quantum Hall state. Again, this will be interesting to study. Overall, there are several topological to topological and topological to spontaneous symmetry breaking transitions that are observed in experiments. These are richer compared to the conventional transitions. I hope I have convinced you of that. There are challenging but interesting conjectures which are rooted in experiments. And I think numerical and theoretical study, at least numerical studies have lagged behind in studying these transitions, and we need them for a complete understanding. I'm also interested in other transitions in other systems like spin systems. So more recently, I have been interested in one-dimensional spin systems and looking at topological phase transitions in those, and also higher dimensional topological phase transitions. That is the end of my talk. Thank you for your attention.
Thanks, Prashant. More questions?
Yeah, you find that for the super universality, you need long-range interactions.
Yes.
Explain. But Laughlin showed that you can his wave functions is exact wave function for short-range interactions.
Yes.
Now you can turn on the long-range Coulomb, and that will not change the ground states, right?
Yes.
Adiabatically.
Yes.
So you need. What I'm saying is that short-range interaction is enough to understand at least the fractional quantum Hall state, at least 1/3. But here you have found that you need long-range Coulomb.
Exactly.
So then how do you explain that?
So the Laughlin wave function is kind of like a fixed point in some, you can think of it as a RG fixed point. So it has very large gap, it has very short correlation length, and so on.
Right.
But yeah, so near the transition, these gaps become smaller. So the Laughlin wave function is not a good approximation.
Oh, okay. Yeah. At the transition, this problem happens.
Near the transition is problem.
Okay. Yeah. One more question I have. So you say also that to understand the Platos, you need these orders.
Yes.
And I find it's difficult to understand in the sense these Landau bands has Chern numbers.
Yes.
And that cannot change if you change the magnetic field or the density of the electrons. So the Plato should exist without disorder.
So for the Plato to exist for the clean case, so let me first mention one subtlety. If you have Wigner crystals, which means spontaneous translational symmetry breaking, you can get these plateaus, but their predictions did not match experiments. So let me just ignore the Wigner crystal for the moment. For the other case, if you were considering Landau level, you will need a gap. So you will need a single particle excitation energy gap.
Right.
But here, to get the plateau, you get it over a range of fillings.
Yeah.
So there is no single particle gap. so what do we have is we have a mobility gap. So we have gap to extended states, but no gap to any excitations at the plateaus.
Okay. Okay.
Yeah.
So Srijit, you can ask, and then Rasti.
Prashant, when you say Z or transition to Z2 and Z3 ordering, you mean that the 3 magnetic length periodicity of the FQHE is converted to a 6 magnetic length periodicity? Is that?
Yes, yes. So it's very similar.
Okay. And in that case, so what are you tuning that changes the transition from FQH to Z2 as opposed to FQH to Z3?
Yeah, thanks for that question.
So
assume that the stripe state has some physical periodicity. Like I showed that we had five magnetic lengths for the stripe state. That's here, the cyan. Now we are doing this calculation on a cylinder. And on a cylinder, we have this single particle wave functions, which they form a lattice. And the separation between these lattice points is inversely proportional to the circumference of the cylinder. So now
in the physical system, then the transition will be from FQHE to some Z subscript, some large number.
Yes, and that n will increase to infinity as you increase the circumference.
Yeah, that's clear.
So basically, there are 3 n orbitals, 3 n single particle orbitals in one period of the stripe state, and that n increases as the circumference goes to infinity. And then we can compare with one-dimensional models if our exponents match with those one-dimensional models.
So Prashant, you mentioned at some point you started the 2D electron gas and you went to Dirac.
Right.
And you said, I'm in the lowest Landau level. It's basically same. They are not quite same because their wave functions are very different. And many of your arguments crucially depend on having zero modes and so on, so forth.
Yes.
So how would you justify this statement? Because if I just did a 2D electron gas, I would not get those zero modes.
Yeah, let me give an answer to that question. So one thing, if I consider Dirac electrons, so the electron side, and I put it in a large magnetic field, and I project to the 0th Landau level, I project both the disorder and interactions to the 0th Landau level, it is going to look exactly like a non-relativistic electron. The wave functions are identical, basically, for that case. But if I consider now, this is one answer, then you can convert that to Dirac composite fermion theory. The second thing, we can also start with the non-relativistic electrons in a magnetic field and then project to the lowest Landau level if you want. Then you can get a non-relativistic composite fermion theory. And then what we have shown is that in that case as well, when you add disorder, you get exactly the same picture with just one component wave function of composite fermion. The reason is that when you add disorder, what you get is a G equal to 2 theory of involving disorder, and G equal to 2 or gyromagnetic ratio equal to 2 theory is square of Dirac Hamiltonian. Just one component of the square of Dirac Hamiltonian. And then you can show that there will be 0 modes, and even in that case, there will be exactly the same wave functions. And the counting works. Exactly, it's exactly the same. The nice thing is that that's already regular, it doesn't have parity anomaly. But we have, so in fact, when I showed you some exponent nu equal to 2.56 for our mean field calculation, that was for that G equal to 2 theory. Yeah. Can you, I don't remember that. Right. Yes. I think that was clean. That was at 0 chemical potential. But they were at 0 chemical potential. Is that right? So this is different.
They were at the neutrality.
This is different because you have finite density of states at the chemical potential.
I see. Okay.
Yes.
Okay. Thanks.
We expect them to be in different universality classes.
Loganagam, you can unmute yourself and ask.
Yeah. Hello. Am I audible?
Yeah.
Yeah. Okay. So this is a question about the statement about there being a universal dissipative effects and so on.
Yes.
I was trying to understand the statement. So in this composite fermion picture, should I suppose that it is also valid for transport and so on and so forth, in the sense that, like, am I supposed to do like kinetic theory of composite fermions to calculate things, or like, is that a valid way to think about these things?
Yes. So that's our argument, that composite fermion theory is a better theory to start with to compute all the transport.
But do you just think the kinetic theory will just be valid? Just you can just do some.
I do not know how to do it, but yeah. So you should start with composite fermions and do transport using that.
Okay. Because like you mentioned something like Wiedemann France and so on, but that is really a very kinetic theory kind of.
Yes, yes. Right. So actually, I do not know what will happen to Wiedemann-Franz law. At the mean field level, you can kind of expect that perhaps Wiedemann-Franz law holds, but when we add these gauge interactions, flux interaction, we don't know the answer.
Okay.
So Prashant, Ajit has a question which you can read or I can read out. From the numerics, how does one tell the stripe apart from the nematic? Does one just look at the magnetoroton excitation and see whether it closes at wave vector q equal to 0 for the nematic or finite q for the stripe? And has this been seen in the 7/3 numerics?
Yes, we have done that. So my slides are. So my laptop shut down.
Okay.
But we had a picture where we had a plot of this magnetoroton spectrum, and then as we increased anisotropy, that magnetoroton spectrum became gapless at some finite wave vector. Yes, so that's what exactly happens.
Yeah. Okay. Other questions from people online or here? Okay.
So when you talked about this fractional quantum Hall to the stripe transition, you ignored the disorder, right?
Yeah, it was clean. I mean, if I have disorder, then translational symmetry is broken explicitly.
Yeah.
Right? Okay.
So I think in experiments, of course, the disorder will pin those stripes.
Yes.
So you will not get the uniform pattern. That is what the experimental observation is. There are uniform patterns, or which led you to think about this is like a disorder free.
Yeah, so the motivation is we should start from a simple theory and then perturb towards experiments. Here, it's appeared that clean point was the better starting point, and then perhaps try thinking about pinning and so on.
So experimentally, you see different kinds of
Experimentally, no, we don't know. So that's the thing. They just saw something, some anisotropy in the resistivity, but they haven't looked at. It's hard to do in gallium arsenide. The two-dimensional electron gas is buried inside a heterostructure. It's hard to look at the densities directly.
Sorry, just to follow on that. So do you have a composite fermion theory for this transition?
We have some proposals. So, and in terms of it is in terms of composite boson. So if you attach 3 flux quanta to electrons, then that gives you a composite boson.
Okay. So, okay, I know elements of that, but the question that I want to ask is that how do you figure out the spatial symmetries of this composite boson?
So you will have a translation symmetry. So we start with that.
So you take the projective group to be manifestly translation invariant.
Right. Yeah.
I see. Okay.
We have
Thanks.
magnetic translations.
Yeah. Okay. Yeah.
Yes.
Thanks.
And then we can look at the condensation at finite wave vector.
I see. Okay. Other questions? Okay, if not, let's thank Prashant once more for the nice colloquium. And tomorrow, Prashant's seminar is at 3:45 p.m. here. Okay, thanks.